We will now consider a final example with forced oscillations, but now we're going to add some damping. So we're going to consider the forced mass spring system x double prime plus 2x prime plus 4x equals 4 cosine 2t. Now we're going to drive the system at a natural frequency of 2, which would have been the natural frequency of this system if we had not added this damping term. So this is the same as the example in the previous video, except for now I've added the damping. So let's look at solving this differential equation. So we need to find both the homogeneous solution and a particular solution to solve this non-homogeneous problem. So first, for the homogeneous problem, we're going to want to look at what the characteristic polynomial is for this system. That is lambda squared plus 2 lambda plus 4 is equal to 0. So that tells me, using the quadratic formula, that lambda is going to equal minus 2 plus or minus the square root of 2 squared minus 4 times 1 times 4 all over 2. So this is actually going to be minus 1 plus or minus the square root of 4 minus 16 is going to be negative 12 over 2. So we can rewrite that as the square root of negative 3. And then we can rewrite that as I times the square root of 3. So that tells us that our homogeneous solution is going to be C1 e to the minus t cosine of the square root of 3 times t plus C2 e to the minus t sine of the square root of 3 times t. So we've added a little bit of damping, which gives us a homogeneous solution that is an underdamped oscillator. Now we want to look for a particular solution. So for the particular solution, we're going to make the guess of A cosine of 2t plus B sine of 2t. Now we can see that the natural frequency of the system is actually going to be square root of 3 because of that damping. And so we don't have to worry about the particular solution being in the homogeneous solution. Okay, we're going to want to substitute this particular solution into the differential equation. So we're going to take the derivative. Okay, so the derivative is going to be minus 2a cosine or sine of 2t plus 2b cosine of 2t. And then the second derivative is going to be minus 4a cosine of 2t minus 4b sine of 2t. And I find it helpful to write that as minus 4 times the particular solution. So let's substitute that back into our differential equation. So we have xp double prime plus 2xp prime plus 4xp. And so that's going to end up being p double prime is going to be actually minus 4xp plus 2xp prime plus 4xp. So those xp's are going to cancel. And that's just going to leave me with 2xp. So that tells me that 4 times cosine of 2t, that's the right-hand side, is going to equal 2 times xp. So that's going to be minus 4a sine of 2t plus 4b cosine of 2t. Now, I'd like to match the cosine terms and the sine terms. I'm going to try to match the sine terms here, but I don't see anything over here. So that's going to tell me that a is going to be 0. And then I want to match these cosine terms there. So I'm going to get that a is going to be 0. And then I'm going to get that 4b is going to equal 4, or b is going to equal 1. Okay, so that gives me my particular solution. It's just sine 2t. So my general solution is going to be the homogeneous solution, x of t equals c1 e to the minus t cosine of square root of 3t plus c2 e to the minus t sine of square root of 3 times t, and then the particular solution plus sine of 2t, because b is equal to 1, and the cosine term goes away because a is equal to 0. Now, something that's interesting that we should look at is that the limit as t goes to infinity of x of t is going to be just sine of 2t. And so sine of 2t has a name. We're going to call that the steady state. Sometimes that limit as t goes to infinity we call the equilibrium solution. But this is not an equilibrium because our system is still oscillating, but it's oscillating at that steady state. So that means as t goes to infinity, the natural frequencies that are governing the system are damped. They're actually underdamped. And so eventually they die out, leaving us just with this steady state. So the part that has to do with the natural frequencies of the system, that's not the forced oscillation, that solution is called the transient solution. And the transient solution is going to die out over time because it decays exponentially, leaving us just with the steady state. And notice that the steady state is at the same frequency as the forced oscillation. Okay, so what's going to prevail in this system is going to be the same frequency as the forced oscillation. Since the system is damped, the natural frequency dies out through the damping, and we're just left with that forcing frequency. And you can see in the graph below that initially this system oscillates with a combination of the transient solution and the steady state solution, but the transient solution decays, and so we're just left with the steady state.